this is our setup. Now we have used our breakboard and we have used a digital lab trainer to make the work easier. So in our circuit we have used 3 chips. That is the 7404 chip, which contains the NOT gates, the 7432 chip, which contains the OR gates, and the 7408 chip, which contains the AND gates. Each chip, as you can see, is connected to a 5-volt power supply, and also each chip is connected to the ground. Now these chips require a 5-volt nodal voltage in order to operate. So according to our truth table, we should get an output that is shown by this light bulb lighting up. So this light bulb will light up if it's 1, and it will not light up if it's 0. We should only get an output 1 for A and B. That is, A and B is 1 and C is 0. For other inputs, as you can see here, we won't get we will get a 0 output, except for A and B equals 1 and C equals 0.
I am Yuga, and I will be explaining how this setup works. To start with, the component we use in the breadboards are 3 NOT gates, 2 OR gates, and 1 AND gate. This is the serial number for our 7408 AND gate, and this is the serial number for our 7432 OR gate. Lastly, this is the serial number for our 7404 NOT gate. Each chip contains 4 gates, therefore it is referred to as quad gate. Operating voltages of each IC and all inputs are 5 voltages. The logic circuit diagram as shown here corresponds to the truth table shown. Now I'll be explaining how the logic circuit diagram works. So as you can see, the Boolean algebra equation for the logic diagram is open bracket A bar plus B bar close bracket plus BC over bar, which can also be further simplified to X equal to A, B, C bar. So let's go over to our logic diagram. I would like to take A equals to 1, B equals to 1 and C equals to 0, where binary number 1 corresponds to high voltage and binary number 0 corresponds to low voltage. As you can see, for A and B, the NOT gate turns the binary 1 to both 0, as the overbar of 1 is 0. As for our first AND gate, we can see that the input 1 from B and input 0 from C gives a 0, as AND gate's output is the product of these two binary numbers. The OR gate on top, which takes in the two inputs of binary number 0, gives an output of 0, as OR gates sum the binary numbers. Then both outputs from OR and AND gate, which are 0, gives an output of 0 at the last OR gate, and eventually the last NOT gate inverts this output 0 into 1, therefore lighting up the bulb. As we can see from the truth table, only when A equals to 1, B equals to 1 and C equals to 0, the output will be 1, where the bulb lights up. For the rest of the inputs, the bulb will not light up. So that is how this logic circuit works. Thank you.
Okay, so now our job is to find the float value of our system. What is float? Float is the value you get once you remove a wire. So to demonstrate that, first I will turn our A value into 1, and then I would take out or float the value for B. As you can see, our output is 1, which means the value of B is also 1. Once I plug it back in, the value seems to go, which confirms our hypothesis that the float value of our circuit is 1. The problems we faced during our project was primarily the disconnection of wires, and due to this disconnection, we kept getting wrong outputs for our values. To circumvent this problem, we simply used the float values of our circuit. As we all know, and we have previously demonstrated, that our IC always gives a value of 1 when any of the inputs is disconnected. We use this and our LEDs to diagnose which values were 1 regardless of our input, and hence we were able to deduce the disconnections of inputs. That is how we circumvented the primary problems that we faced.